Okay, so 4.3, graphing radical functions. Now, radical functions is very vague. That could mean a function with any index in the radical. But we're going to be focusing on two different functions today, the square root function and the cubed root function. And the first thing that we're going to do is we're going to look at the parent function for each one of these, talk about transformations. How does it shift up, down, left, right? What does a stretch look like? How do I find a stretch? And really, that's going to be the whole focus of our lesson. So kind of circling back around to all of those ideas, just doing it now for another different kind of function. So example 1, graph the parent functions below, state the domain and range, and whether the graph is increasing or decreasing. So this first one, f of x is equal to the square root of x. This is the parent function for square root. I know it's a parent function because I only have the argument and whatever operations operating on that. So the square root of x, I don't have plus or minus or times anything else. And it's square root because I don't have any other number in the index position. When we look at new types of functions, we like to make a table and kind of get a real good idea on what these look like. So when I look at these values of x and I plug them into my function, right, my square root of x function, when I plug in the square root of -1, well, that's just imaginary. That doesn't give me a real value of y. I can't graph that on an xy plane, on a real number plane. Square root of 0 just gives me 0. The square root of 1 gives me 1. The square root of 2 gives me 1.414 something, 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 something. It's not a perfect square. As I graph these, I'm going to be looking for those perfect square numbers. So that's why I skipped 3. 3 is also not a perfect square. I don't really want to graph those decimals 1.414. That's too hard to estimate. So I graphed the square root of 4, which is 2. And then I skipped all the way down to 9, because 9 is the next perfect square, which gives me 3. My graph's a little on the small side. I'm going to zoom in a bunch there. And I'm going to plot all these points. Now, if I try to go to the left-hand side of the y-axis over here and my negative numbers for x, these are all going to be imaginary. So it doesn't matter if I plugged in -2, -3, -4. Those are all imaginary numbers. And when I plug in things that are positive or neutral, I get this slowly increasing graph here. I could continue to plug in bigger numbers, right? The next perfect square is 16. Square root of 16 is 4. I could plug in 25 and get 5. So this graph will continue on to the right indefinitely. The additional parts of this prompt ask me to state the domain, the range, and whether the graph is increasing or decreasing. So looking at domain are all the possible x values. So as I look to the graph to the left, it does not continue forever. It actually hits 0 and does not exist on the left-hand side. And then it does continue on the right-hand side forever. So when we're talking domain, we're talking left and right, it starts at 0 and goes to positive infinity. Now there's different ways that we can write domain and range. I'm going to use inequalities here. So x is going to be greater than or equal to 0. If you were to write that in interval notation, you could write 0 to infinity. They're equivalent expressions, equivalent ways to describe. Now for the parent function, the range, when I look down to the negative, does not continue down. It actually just starts at the origin, but it does go up. Now it goes up slowly, but it does continue to increase. So my range is also going to be greater than or equal to 0. But when we're talking range, make sure you've got a y in there. If you wanted to write it in interval notation, it would again be from 0 to infinity. And then talking about increasing and decreasing. Increasing and decreasing is asking, as the graph goes to the right, is this going up or down? So as I travel along my graph and I walk from left to right, this graph is going to continue to go up, 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 up. Now it's going to go up at a very slow rate, but it is going to increase constantly. All right, cool. So then we're going to do the same thing for the cubed root function. And I know I'm taking cubed root here, so I'm going to strategically pick some numbers that I can actually take the cubed root of, just so I get whole numbers when I plug it in. All right, so when I plug these in, let's see. The cubed root of -8. Now, when I'm doing cubed roots or any odd root, I can have negative numbers underneath there. Because this is asking what to the power of 3 is -8. And I can put a -2 in there. All right, and similarly, when I take the cubed root of -1, I just get -1 because -1 times -1 times -1 gives me -1. The cubed root of 0 is 0. The cubed root of 1 is 1. And then the cubed root of 8 is 2. Now I can look at bigger numbers. This will give me enough of an idea. All right, -8, -2. Let's go ahead and plot these points. -1, -1, 0, 1, 1, 8, 2. So here's the cubed root parent function. Big difference between square root and cubed root is that The cubed root function goes left and right forever and up and down forever. All right, so domain, when I look to the left of this graph and to the right of this graph, I can continue to plug in negative numbers. That's fine for cubed root. That's allowable. I don't get anything imaginary. I get real numbers. I can continue to plug in whatever negative, positive numbers I want. Therefore, this is going to be all real numbers. And the range. Now, this graph increases and decreases very slowly, but it still will go down for always and up for always. So again, all real numbers. There's no stopping point. There's no holes. There's no asymptotes. And as I look to the graph from the left to the right, if I follow this, it just goes up and up and up and up and up. Now, it goes up at a different rate. So it goes up a little bit at a time, and then it gets a lot faster and steeper, and then it levels back out. But it's still an increasing function. All right, some more notes for you. So this is kind of generalizing the transformations of a radical function. A radical function is of the form f of x equals a times the nth root of x minus h plus k, where a would identify a stretch or a shrink, h causes a horizontal shift. Again, if h is positive, it moves to the left. If it's negative, it moves to the right. K causes a vertical shift. And while the index can change, the value of n can change, it's not going to cause a transformation because it's going to cause a different graph. So n will determine the shape of the graph, which we saw above. If it's a square root, it has a starting point, it just goes up to the right. The cubed root, the domain is all real numbers. So we're going to graph using transformations. And then in example 3, we're going to name transformations. So there's different ways you can do this. You can make a table of values. I think the easiest way is to just use the parent function as reference and then move the points. So that's what I'm going to recommend. So on each one of these graphs, I'm actually going to graph two things. I'm going to graph the parent function because I'm going to get really good at that. And then I'm going to just move that accordingly. So first thing to notice about problem A is it's a cubed root function. So I need to use the cubed root parent function as my base, as my home, as my point of reference. You could memorize these. You could rework them every time. You could do them once on your paper and then just reuse them. I tend to just memorize them, but that's what works for me. So I'm just going to go back to the cubed root, and I'm like, okay, wait. I want the table for the cubed root function. So I could plug it back in if I wanted to, or I could copy it from above. Right? The cubed root of -8 is -2. The cubed root of -1 is -1. And I get these values. So I'm going to graph the parent function, and then I'm going to move it. So if you're using pencil, you might want to do like one in light pencil and then make one kind of darker. If you're graphing, if you do your notes in different colored pens, you might want to use different colored pens. I'm going to do my parent function in this pencil and see if you guys can see it. So -8, -2. It's the same graph we just did. So this is my pencil tool. And then let's talk about how this function is different from the parent function. So the parent function is the cubed root of x. Anything that's not that causes some kind of transformation. So I have a plus 1 under the radical, and then a minus 2 outside the radical. All right. Well, what we know about functions is whatever I add or subtract inside the argument causes a horizontal shift. The plus 1 is actually going to move my graph left 1. It's always going to be the opposite. Whatever I do to x is always going to be in the opposite direction. And the minus 2 outside the radical is going to shift this down 2. I don't have a change in A, so I don't have a shift. I don't have a stretch or a shrink or a reflection. Just a shift. So now I'm going to take each point that I already plotted, and I'm just going to go left 1, down 2, and replot it and get a new graph. Left 1, down 2. Left 1, down 2. Left 1, down 2. Now, if you were doing this on the test, I would say either label each one of them or maybe lightly erase the parent function, or just make sure that your answer stands out somehow. So my suggested graphing method is to graph the parent function and then perform the transformations point by point. I think this is the easiest way to do it. You could also just create a new table for this parent function. You just have to be mindful of the points you're plugging in unless you want to graph a bunch of decimals. All right, cool. So B, we'll do it again. So B, calling this g of x equal to the 2 times the square root of x plus 3 all plus 1. I forgot to do domain range and increasing and decreasing for the last problem, so I'm going to go back. Sorry. So now we're looking at domain and range for the actual function that I was asked to graph, which mine is like kind of this purpley color. So when I look left and I look right, domain continues on in both directions, left and right. So this is going to be all real numbers. The range, again, this graph will go down forever and up forever, so all real numbers. And my orientation of the graph did not change, so I'm still moving up and to the right, so it's still increasing. Really not any change of information from the parent function. Now we'll go on to the next example. Once you've created this table once, you can just copy it from wherever you have it, or you could just memorize it to recreate it. So I want numbers that I can take the square root of. If I try -1, I get something that's imaginary. If I try 0, I get 0. If I try 1, I get 1. If I take 4, I get 2. If I try 9, I get 3. That's just for the parent function. So I know which parent function I have to use by looking at what I'm given. I have the square root of something. So that means I have to associate it with this function. Square root function. The square root function does not exist when x is negative. So again, I'm doing this in this kind of light gray color so that it doesn't stand out, because this is my parent function. It's not necessarily my answer. It's just going to help me get to my answer. There are 3 pieces of information that change this from the parent function. There's 3 transformations happening. When I have the argument and I multiply on the outside of the operation by 2, that causes a vertical stretch. And that's caused by this 2 right here, vertical stretch of 2. See if you can jot down before I tell you, what does the +3 inside the argument and the +1 outside the argument do? Or at least just think about it in your head for a few seconds before we write it down. All right, so the +3 underneath the radical is going to shift left 3, and the +1 on the outside is going to go up 1. The shifting of points is not too tough. We do need to be aware of the stretch also, though. Vertical stretch means the distance vertically is going to double. So this initial point 0, 0 is kind of my anchor point. It's going to shift left 3, up 1. And since it's my first point, there's no stretch that's going to change it. Left 3, up 1. But the next one, I want to stretch this distance. So when I move this point 1, 1, left 3, and then up 1, I get negative 2. But then I want to double this distance. The distance here from vertically is 1. I want to double that to 2. So first this point moves 1, 2, 3, and then up 1. But then I have to double this distance. So instead of going up 1, I'm going to go up 2. So I have 4, 2. So I moved left 3, 1, 2, 3. I go up 1. But instead of an up 1, I need to go up. Oh, wait, let me not goof this up. I got to double that distance again. Okay. So the distance from the initial point to the new point that I'm moving is 2. I want it to be 4 now. So let's see. I move this 1, 2, 1, 2, 3, and then up 1. This was up 2 from the initial point, so now I'm going to go up 4. So this point's going to be right here. 1, 2, 3, 4. And then 9, 3, I go left, 1, 2, 3, and then up 1. The distance here from my initial point to this point was up 3, right? I want to double that. I want to stretch it to 6. So from here, I've got to go up 6. 1, 2, 3, 4, 5, 6. Oops, wrong color. The stretches do make it a little bit more complicated. We will be keeping those to a minimum. We won't be doing them a lot. But you can tell that this graph gets bigger faster, and that's because of the 2. Our domain and range are going to change this time. So when I'm looking at x values, this actually hits at, what is that? That's negative 3. So negative 3 to positive infinity. So x is greater than or equal to negative 3. And the range value hits right here at 1. So it's going to be 1 and above. As I follow this graph to the left, it is still increasing. Now I know that all the graphs, the parent functions and the transform functions that we've looked at so far have been increasing, but they can change. If I were to have a reflection across the y-axis, you can kind of imagine what that would look like. This graph would actually be decreasing as I go to the right. So it can be decreasing, right? Same thing for square root or cubed root. We just haven't had any reflections. Example 3, rewrite to identify the transformations from the parent function. So we'll be rewriting these and then describing the transformations. Okay, I'm going to scroll back up momentarily. You'll notice that when I look at this, the transformations of a radical function, I never have a number right here in front of x. So my goal is to put it just like this, where I have the radical of x plus or minus a number, and any coefficient gets moved in front. So that's kind of what this process is all about. It's going to require a little bit of factoring, a little bit of splitting up. So that's my goal. My goal is that whatever is here, I'm going to bring out in front. So example 3a, pretty basic example here. I'll just give you a reminder that it is true that if I have, let's see, the square root of a times b, that I can rewrite that as the square root of a times the square root of b. And that's kind of what I'm going to use here. Problem A, h of x is equal to the square root of 9x. There's really nothing to factor per se here. I am factoring the 9 out, but I can think of it as just splitting up also. When I take the square root of 9, when I take the 9 out, I get 3 times the square root of x. This is an equivalent function. It's just rewritten in a different format. And this format lends itself to describing the transformations. That 3 in front is the a value, which causes a stretch or a shrink. Because the value is greater than 1, this causes a vertical stretch. With a factor of 3. Or a vertical stretch of 3 works. And that's the only transformation this problem has. I don't have a plus or a minus anything, so I'm not shifting up, left, down, right. Well, A is easy enough, but B adds another layer. I can only factor something out if I can take it out of everything. Now here I only had one term, so factoring out was more like splitting up. For B, I have f of x equal to the square root of 4x plus 16 all plus 7. I have to be able to take 4 out of both of these terms. So as I rewrite, I can take out the GCF. I can take out the 4. And that's the key here. You have got a few of these in your Savas assignment, but that's the key here, is to recognize that I could take a 4 out of both of these terms. And then if I have 4 times something, it's the same thing as taking the square root of 4 times the square root of something. Now the square root of x plus 4 I'm not going to touch, but now, oh, this is a perfect square. How beautiful. The square root of 4 is 2. And this time I have 3 transformations to describe. So the 2 in front is larger than 1, so that causes a vertical stretch. So vertical stretch of a factor of 2 or vertical stretch of 2. The adding 4 under the radical means this is going to shift left 4. And then the number outside the radical, I have a plus 7. This is going to shift up 7. Sorry, might be too fast. Slow down. The rewriting part is important. If I didn't rewrite this transformation would look a lot different. All right, so the last example gives graphs and asks for the equations. So I know that it's tedious to write these graphs down. The way that I graphed this in Desmos, counted each box as a half. So I'm going to zoom in a whole bunch so you could accurately copy that down. So I've got a coordinate plane here. The starting point for this function is -3, -4. It increases. You can tell here that it hits this point, -2, -3. It also hits and identifies 1, -2. Try to make it at least hit those points and then make it as accurate as possible. And from there, we're going to write the equation. So the method we're going to use here is we're going to identify the type of function, find the shifts, and then find A. The last part takes some algebra. The rest of it's pretty not very labor intensive. So identify the type of function. Step 1. Does it look like a square root or does it look like a cube root? Well, square root functions don't continue across the whole domain, have a starting point, and then they continue either to the right or the left. So this is going to be a square root function. And then I can find out the transformation just by looking for that anchor point. So for a square root function, that anchor point is going to be my starting point. For the cube root function, it's going to be where this graph changes directions. So my starting point, instead of being at 0, 0, is at -3, -4. So I can tell that that's left 3, down 4. So I'm going to start writing my parent function, but it's not going to be perfect. Remember that, or I'm sorry, not my parent function, but my equation for this function. So I can call it f of x, I can call it y, I can call it g of x, I can call it whatever I want on the left-hand side. I don't know a. Left 3 is going to look like plus 3 under the radical, and then down 4 is going to look like -4 outside the radical. So that takes care of 1 and 2. Now I have to find a. This is going to take some algebra. To find a, I'm just going to plug in some point to find a, just like we've done for quadratics. Now you can plug in whatever point that lies on here that you want. There's one clearly identified, so that looks like a good one to pick. So I'm going to plug in some point. I'm going to pick 1, -2 to find a. So f of x is the same as y. I'm looking for a. And this is just going to use some order of operations. Order of operations is I've got to do what's in parentheses first. The square root acts as parentheses. I take the square root of 4. Square root of 4 is 2, and I just wrote it in front. So I get an a as 1. So when I rewrite my final answer, now that I know a is 1, I know the equation of the graph is just this. That's for a, not for b. Okay, so going over one more time what I did. First, identify the shape. All right, well, because it has a starting point, it's going to be a square root function. Then I identified the shifts, which was pretty easy because instead of starting at 0, 0, it starts at -3, -4. So it's left 3, down 4 from here. And then I did some algebra to find a. And we're going to do the same thing for b. So I'll zoom in and let you jot that down. This is kind of like a snake kind of shape, which is indicative of a cubed root function. Again, I graphed this on Desmos and I counted each block, each square as a half. It's not marked on the graph, but here's another good point. Now, the anchor point for a cubed root function is going to be that point where the graph changes direction, right? From convex to concave. Or if it's going the other way, concave to convex. Namely, I'm tracking this point. I want to know where that moves because that used to be at 0, 0, and now it's at 1, 2. So this goes right 1, up 2. It's a little easier to look at the numbers than it is to look at the squares because they don't use each square as 1. Now, this is a cubed root function because it goes to the left forever and to the right forever. It has kind of these snaky shape to it. So it's just the same as above, except for my index now is 3. So plug in the obvious transformations, the shifts, and then we'll find A. I don't know A yet, so I'm going to leave A as A. Right 1 is going to look like a minus 1 under the radical. And up 2 is going to look like plus 2 outside the radical. When you're writing these, be really careful to make sure that it looks like the plus 2 is outside the radical. Either make sure that this ends really clearly, put a little space in between. It's tough when I see answers that are like this, and you're like, did they mean for that 2 to be under the radical? It's supposed to be outside the radical. Just make it really clear. It's easy to do. Guilty of it myself. I'm going to find A. To do that, I'm going to plug in some point for x, y. Well, you can pick any point you want that's on the graph. For me, it makes sense to pick the other point that they give me because I know for sure that it's there. So I'm going to use 0, 1. Then plug 1 in for y. I'm looking for A. X is 0. And then I simplify. Order of operations says I have to do what's in the parentheses first. This radical sign acts as parentheses. It's a grouping symbol. 0 minus 1 is negative 1. Okay, now reminder, I'm doing cubed roots, so it's okay if I have negative numbers. The cubed root of negative 1 is just negative 1. And solve for A. So I subtract 2 from both sides. And if I were to divide both sides by negative 1, I just get A is 1. So again, A is 1, so the number in front of the radical is just going to be 1, or you could write nothing there. That wraps up 4.3. It's a lot.